Welcome back, students. In this video segment, we will cover section 2.2, right triangle trigonometry. Section 2.1 really wasn't at the heart of the course. Section 2.1 just involved a discussion, a rather long discussion of angles and how we measure them. And we found that in calculus, the best way to measure angles is in radians. And again, if you don't remember why, it's because radians have no units. So a lot of our work in this course has to do with measuring angles in radians. So at this point, it's hoped that you have a really good grasp of how to divide up the angle pi into subdivisions like pi over 6, pi over 3, pi over 2, etc. And you're able to do that independently of thinking about angles measured in degrees. So in this section, we really begin trigonometry and what trigonometry is all about. Trigonometry is about measuring things in our universe using triangles. So at the heart of trigonometry are six things, six what are called trigonometric functions, the six trigonometric functions. So to get at the six trigonometric functions, we start out with a right triangle, and we label the angle in the lower left-hand corner as, say, theta. And then we label the measures of the sides as A and B as the two legs and C as the hypotenuse. Then we dig into the six trigonometric functions of theta. Okay, so you see it spelled out. These are the six trigonometric, which we're going to abbreviate to trig, the six trigonometric functions of theta. Okay, and they start with the first trigonometric function called the sine of theta. The sine of theta is abbreviated as SIN theta, and it equals B over C. Okay, and there are five others, and this goes painfully slow at first, but you're going to get used to these trig functions very, very quickly because they happen. Other than our discussion of angles in 2.1, they happen everywhere in trig. So the next trigonometric function is called the cosine of the angle theta. And the cosine of the angle theta is abbreviated cos theta, and that's equal to A over C. So it looks like the trigonometric functions are really fractions. And sometimes that's the case. We have to kind of be careful with using the word fractions because fractions typically, actually not typically, but fractions always have only whole numbers in numerator and denominator. And some of these fractional values have radicals in them, like radical 2 or radical 3 and stuff. So they technically, they're not fractions, but they look like fractions. So let's look at the third one. The third trigonometric function is called the tangent of theta. The tangent of theta is abbreviated TAN theta, and that's equal to B over A. Now, of all six of the trig functions, these are the most important. These are most important for a whole bunch of reasons, primarily that the other three trig functions can be written somehow in terms of these first three. If that didn't make sense, you can let that go. But just to let you know, these are the most important of the six trigonometric functions. If you take a calculus or a physics book and you sort of randomly open to any page in the book, you're highly likely to see one or more of the three, sine, cosine, or tangent of theta. Of these three, the most important two are sine theta and cosine of theta. Why? Because the tangent of theta, and you'll see that real soon, can be written somehow in terms of both the sine and cosine of theta. So if we know sine and cosine, we can somehow figure out tangent. That idea is a very, very important idea, the idea of being able to find the value of a trig function by being given one or more of the other trig functions or different trig functions. Now, of those two trig functions, sine and cosine, singly the most important trig function in all of STEM field mathematics and physics is the sine function. The sine function. And again, for the same reason, if we know the sine of theta and maybe one more small detail about the angle theta, we can find the value of cosine theta. And if we know sine and cosine, we can find tangent. And if we know all three of these trig functions, we can find the other three trig functions. So if you got lost in that, don't worry. We're going to continue on with the other trig functions, the other three trig functions. The other three trig functions are the cosecant of theta. And the cosecant of theta is abbreviated as CSC theta, and it's equal to C over B on the triangle. The next trig function is called the secant of theta. The secant of theta is abbreviated as SEC theta, and that's equal to C over A. And finally, the cotangent, and as I'm writing the word cotangent, I'm looking over at the word tangent that I wrote, and it's misspelled. I'll fix that. Cotangent of theta, and that's abbreviated as COT theta, and that's equal to A over B. Okay, so I'm going to go back and I'm going to fix up my spelling of the tangent of theta. So with the help of my pause button, I fixed my spelling, and I kind of got a little chuckle out of it because the word tangent is not only central in trigonometry, it's central to all of calculus, and I can't believe I misspelled it, so yeah, not a good thing. Okay, so we have the 6 trigonometric functions and their abbreviations. We almost never write out the names of any of the 6 trigonometric functions. We use the abbreviations almost all the time, unless we're writing a sentence or something. When I want to talk about a trig function, I'll spell it out as a word. Okay, so let's take a look at our very first example of using the 6 trigonometric functions. And a very simple example. So for example, the example is to find the value of each of the 6 trig functions. Find the value of each of the 6 trig functions. 6 trigonometric, which we always abbreviate to trig, T-R-I-G. We can take the period off that too. The 6 trig functions of the angle theta pictured. I'm going to draw an angle theta. Okay, so in order to draw an angle theta, I got to kind of draw a triangle. So here we go. Here's a right triangle in particular. So here's our right triangle. Okay, and let's say here's theta, here's the right angle, and we're going to label this side, the vertical side here, as 3, hypotenuse is 5. Okay. The first problem we notice, and it's kind of an obvious one, is that we have a side missing. Now this is where your geometry comes in, and I'll help you out here a little bit if you've forgotten. We have a right triangle, we're missing one side, and we have available to us something called the Pythagorean Theorem, which we use an awful lot in calculus and stuff. So This is also a popular triangle in geometry, so see if you can remember what the missing side equals. The missing side is side of length 4. Now, if you forgot that, just substitute a variable for the horizontal side and use the Pythagorean theorem. The Pythagorean theorem says a squared plus 3 squared equals 5 squared, so a squared plus 9 equals 25. Or a squared, if you subtract 9 from both sides, what's 25 minus 9? 16. Take the square root of both sides, positive square root, and you get a equals 4. So what we're looking at is something that in geometry we refer to as a 3, 4, 5 triangle. So here's our completed 3, 4, 5 triangle. It's a right. Of course, it's a right triangle. With the exception of a couple of sections in this course, all of the triangles will be right triangles. We're looking at right triangle trigonometry for the most part in our course. So we have 6 things to look at. We have 6 things to look like, 6 trigonometric functions. The first one is the sine of theta, sin theta, and that is 3 over 5. If you recall, up above here, that's too far up. If you recall, up above here, if my surface is going to allow us to look at it, surface is running really slow. Let's see, the sine of theta, and my surface is really acting up. The sine of theta is b over c, okay? Sorry about the technical difficulty there. So back to the sine function. Sine is b over c, so 3 over 5. The cosine of theta is a over c, which is 4 over 5. The tangent of theta is b over a, or 3 over 4. Okay, and just for your reference, I'm using a for 4, B for 3, and C for 5. Okay? All right. So, something I want you to notice about the trig functions. I want to go back, before we find the other 3, I want to go back to the definition of the 6 trig functions, if my surface will allow me to scroll back. Thank you, surface. Look at the sine of theta. The sine of theta is b over 3. And look to the right of that, the cosecant of theta is c over b. The c over b is just the reciprocal of b over c, so the sine of theta and the cosecant of theta are reciprocals. Cosecant of theta equals 1 over the sine of theta. That's what I was talking about earlier about the relationships between the trig functions. There are many, many different relationships between the trig functions. I think in this course there are a total of, at the end of the course, so don't panic, I think there are a total of 75 or 80 relationships between the trig functions that we're going to be expected to know. The next trig function, cosine of theta, look at, that's a over c. The secant of theta is c over a, so the secant of theta is the reciprocal of cosine. And if you think that's going to happen with the cotangent, you guessed it. The cotangent of theta equals a over b, the tangent of theta equals b over a. They're reciprocals of one another. So if you know sine, cosine, and tangents, to get the other 3, you simply take the reciprocals of those first 3 trig functions in order. So let's go down to our problem. We have sine theta, cosine theta, and tangent theta of theta. The next trig function is the cosecant of theta. abbreviated CSC of theta, and that's equal to 5/3. Now, if you're lost in all of this, don't be too concerned. You're going to look back at this in probably about 2 or 3 days. You'll look back at the finding of the six trig functions. You're going to realize it's one of the easiest things to do in the course if you're given values on a right triangle, values of the sides. So the secant of theta is 5/4, and the cotangent of theta is equal to 4/3. This is a very simple example, which may not seem simple right now because you're just getting used to this, but you're going to find that the six trig functions are not as complicated as their definitions maybe look to you right now. I'm going to look at another example, but I'm going to kind of throw a wrench in the works, which means that I'm going to do something here that's going to show us that we really need we need some sort of device for this besides the definition of the six trig functions. We need something to help us out with the six trig functions. So here's our next right triangle, and I'm drawing it really off kilter on purpose. Suppose this is side of length 1, here's the right angle, this is 2, and our angle theta is located up here. And I want the values of the six trig functions again. Well, if we just go on that first triangle up above with the definitions of the six trig functions, we just go with that, we're going to have to reorient the triangle that I have drawn so that theta is in the lower left hand corner, and then go through with the Pythagorean Theorem and find the remaining side. That's not going to be convenient for us. We need to be able to, when the triangle is drawn in any kind of orientation, we need to be able to find the values of the six trig functions without moving the triangle around. Okay. Now we could always move the triangle around, but if you're dealing with a problem where there are 5 or 6 triangles floating around in the problem, it's not going to be efficient for you to be doing that. So let's take a look back at the definition of the not all 6, just the first 3 trig functions, the sine of theta, the cosine of theta, and the tangent of theta. Here is the reoriented triangle the way we had it in the beginning, the right triangle. Here's the angle theta, here's A, here's B, and here's C. Now, just the first 3 trig functions. The sine of theta is equal to B over C. The cosine of theta is equal to A over C. And the tangent of theta is equal to B over A. Okay, that's sort of old news for us now. Now, I want to rename these sides. I want to rename the sides by naming them in terms of the angle theta. We call A the adjacent side to theta. The adjacent side, adjacent. The word adjacent means next to. The side A is next to theta. The side C is called the hypotenuse. So we're going to label it as the hypotenuse. And the side B is the side farthest away from theta. So we're going to call that the side opposite theta. Opposite theta. Okay. Now let's look at the sine of theta. Let's look at all 3 trig functions of the trig functions listed, but let's take a look at the sine of theta just for right now. The sine of theta is B over C, or the opposite over the hypotenuse. The opposite over the hypotenuse. Now I'm going to go one step further with these words, and I'm just going to isolate the first letter of each word. So the sine is opposite over hypotenuse, O over H. The cosine is adjacent over hypotenuse. And the tangent is opposite over adjacent. Okay, I'm going to go one step even further. With the three trig functions listed, I want to look at I'm going to abbreviate further. I want to look at just the first letter of each. So the sine is opposite over hypotenuse. Give me a second here. I want to see if I can get my surface to cooperate. The sine is opposite over hypotenuse. The cosine, my surface is really slow here. I'm trying to get fancy with colors here, and it's not allowing me to. The cosine, okay, let's see if I can do it now. Here it is adjacent over hypotenuse. Cosine is adjacent over hypotenuse. The tangent is opposite over adjacent. Opposite over adjacent. Now say this word out. Say this as a word. Say it out as a word. SOHCAHTOA. Doesn't that sound like a corny word? SOHCAHTOA. SOHCAHTOA. Now, if you think that's funny, it is. And again, if you think it's funny, you're likely to remember it. And this tells you how to identify the sine and the cosine and the tangent of in a triangle. Now, what about the other three trig functions? Well, the other three trig functions, the cosecant, the secant, and the cotangent, are simply the reciprocals, remember, of the first three trig functions in order. So that brings up something else. We're going to want to memorize a whole lot of stuff in this course, and one of the things we want to memorize, one of the first things we want to memorize is the values of the six trig functions in their order, in the same order every time. Sine, cosine, then tangent for the first column. Cosecant, secant, and cotangent for the second column. Okay. So, toa. The sine is opposite over hypotenuse. So, the cosine is adjacent over hypotenuse. And toa, tangent is opposite over adjacent. So let's go back to our triangle. Maybe I'll redraw it for us. Here's the triangle in our particular problem. Here's the triangle in our problem. 1, 2, and there's theta. SOHCAHTOA for sine, cosine, and tangent. Well, we need the third side. The Pythagorean Theorem says that c squared equals a squared plus b squared. Remember, we're using c for the hypotenuse here, so c squared equals 5. 1 squared plus 2 squared is 5. So c, if we take the positive square root, positive because we're looking at a side of a triangle, c is the square root of 5. So c is the square root of 5. That's about the worst square root of 5 I've ever drawn. Okay, I've also drawn it in quite a bad position here. Okay, so I moved our square root over. So let's write out the six trig functions. The sine of theta. The sine is opposite over hypotenuse. So what's the length of the side opposite theta? It's 2. The hypotenuse is the square root of 5. Now I know you have a question now. And if you don't, in another 5 or 6 seconds, a question would arise just looking at 2 over the square root of 5. If a question happens, that means you probably remember a lot of your intermediate algebra. So hold your question for just a minute. You and I both know what your question is. Those who don't know what the question is, I'll let you know. I'll let the cat out of the bag in a minute. So the cosine is adjacent over hypotenuse. Cosine is adjacent over hypotenuse. the side adjacent theta is not radical 5. Radical 5 is hypotenuse. So the side adjacent theta is 1. Hypotenuse is radical 5. And finally, for the first three trig functions, the tangent of theta is opposite over adjacent. So 2 over 1, or 2. Okay. Now the other three trig functions in order were cosecant of theta, the secant of theta, and the cotangent of theta. So you might be thinking, my God, this stuff is just fraction-like quantities, just really doesn't seem, how's this going to connect to the sciences? In a huge way it connects to the sciences. There is no science without the trig functions. We need them. Okay, the cosecant of theta is radical 5 over 2. The secant of theta is radical 5 over 1, which is radical 5, obviously. And the cotangent of theta is 1 over 2, 1/2. Okay. Now you might have had the question pop up in your mind about the sine and the cosine. They both have radicals in the denominator. Now I'm gonna take a little side trip here about the radical in the denominator. It'll only take us maybe a minute to 2 minutes. There are two schools of thought about radicals in the denominator. Some professors absolutely will not allow you to write radicals in the denominator. Some don't care. If you are taking calculus with me, for the most part, I don't care. The radical in the denominator or the radical in the numerator, it's the same, the number has the same value. But some people want that, some people want that radical out of the denominator. So you may not take me for calculus. And if you do take me for calculus, you may not take me for all of your calculus. You're definitely not going to take me for your physics, because I'm not a physicist. So I need to make sure that you're able to survive in any setting. So in my directions, look for the phrase rationalize all denominators, in which case you take that 2 over radical 5, for example. If the problem said to rationalize the denominator, and you do what you did in intermediate algebra, you multiply and divide by radical 5 to get the number in a different form as 2 radical 5 over 5. If in a particular problem I ask you to do on a test, I don't say rationalize the denominator, then don't bother. Or rationalize the denominator anyway. It's up to you. If I don't ask for it, it's up to you. Okay. So let's do another example here. Let's see. Well, rather than digging into another example, let's push forward into the section. You notice so far that there's kind of a blend between geometry and algebra going on, and that's sort of what's going to be going on for the rest of the course. For the next part of the lecture, I want to give you an introduction to what I was referring to as the relationships between the trig functions. I said that the first three trig functions are related to the sine, the cosine, and tangent are related to the last three, the cosecant, secant, and cotangent, in a very specific way. They're reciprocals of one another. These ideas I want to put down as formulas. I want to write down as formulas. These formulas are called fundamental identities. Fundamental identities. In this course, we talk about these things called identities a lot. In fact, I think I said that in this course there are about 75 or 80 of them. I'm estimating here. I think I'm pretty close. And by the end of the course, those 75 or 80 identities are going to be locked up in your head. They're at the absolute core of the language of calculus and physics. Okay, so the first set of identities I want to look at are related to, or actually are formulas that relate the first three trig functions, the sine, the cosine, and the tangent, to the last three trig functions, the cosecant, secant, and cotangent. And you saw me use these first few fundamental identities, but I never wrote out formulas. I never wrote out the formulas. Now remember, the sine is b over c, the cosine is a over c, the tangent is b over a. That's all based on that first right triangle. That looks like a terrible looking right triangle. A, B, and C. And the cosecant, secant, and cotangent were the reciprocals of these three, the first three in order. Cotangent is equal to A over B. So I'm going to write out the first three of that big long list of identities that we're going to have by the end of the course. The first three are called reciprocal identities. The first three identities are called reciprocal identities. Identities. The first reciprocal identity says that the cosecant, remember cosecant is b, or rather c over b, sine is b over c. They're just reciprocals. So the cosecant is the reciprocal of the sine. So cosecant of theta equals 1 over sine of theta. The secant of theta is the reciprocal of cosine. The secant is 1 over of theta is 1 over the cosine of theta. And finally, the cotangent of theta is the reciprocal of tangent. It's 1 over the tangent of theta. Okay. Okay. I want to look at two more identities before we look at another example. Two more identities before we look at a specific example. Take a look at, if you will, take a look at sine, cosine, and tangent. Now with the sine and cosine, imagine putting your finger over or covering up the denominators, c. So you get sine of theta equals b over, and the cosine of theta is a over. Now look what happens when you divide sine by cosine. If you take sine of theta and divide by the cosine of theta, you get b over c divided by a over c. And the reason I had you imagine covering up the denominators is because when you invert and multiply, if you invert and multiply in this complex fraction, the c's cancel out. The c's completely cancel out. And they leave you with b over a. But what's b over a? It's the tangent of theta. Now let's omit all this middleman algebra between sine over cosine and tangent. This says that the tangent of theta is equal to the sine of theta over the cosine of theta. Think about that for just a minute. If I know the sine of theta and I know the cosine of theta and I want the tangent of theta, all I need to do is divide sine by cosine. Okay? Now, since the cotangent is 1 over the tangent, since the cotangent is reciprocal of tangent, that must also give us another identity. It must give us the identity that cotangent of theta is cosine of theta over the sine of theta. Okay? These two identities are called quotient identities. Quotient identities. Now, if you forget the name of an identity, it's not the end of the world. The most important thing is to memorize the actual identity, but the names of the identities, for me, it's not the most important thing. Okay? So before we get moving on, let's use these identities. Let's see how we might use these identities. So, I'm going to do a similar problem, but we're not going to use that we did, but the similar problem to the two-part problem we just did, but the difference is going to be, the big difference is that we're not going to be given a triangle. So given that the sine of theta equals a particular value and the cosine of theta equals a particular value, I want to find the exact values of the remaining trig functions. If you missed that, let me write it out. So here's the example. Suppose somehow we figured out, or we were given, that the sine of theta equals 1/3 and the cosine of theta equals 2 times the square root of 2, 2 radical 2 over 3. I want to use identities to find the exact value of the remaining trig functions. The first thing I think you ought to do is to write out all 6 trig functions in the same order, without writing any values, but all 6 of the trig functions in the same order every time. So the sine theta, the cosine of theta, and the tangent of theta. Next is the cosecant of theta, the secant of theta, and the cotangent of theta. Okay, no triangle here. I'm not going to draw any triangle. We could do this with a triangle. We're not going to. The sine of theta equals 1/3, so I'm going to write that in. The cosine of theta equals 2 radical 2 over 3, so I'm going to write that in. Now, let's look to the right of the sine of theta, the cosecant of theta. The cosecant is the reciprocal of the sine. And notice, I didn't have to think about the identity, the particular reciprocal identity above. I didn't have to think about it, because I have the 6 trig functions memorized in the same order. I use that first reciprocal identity without having to refer to it, just by knowing that the last 3 trig functions are the reciprocals of the first 3 in order. And the same for the secant of theta. The secant of theta will be 3 over 2 radical 2. And just for a little practice, if you were asked to rationalize the denominator, you would multiply numerator and denominator by radical 2. And you would end up getting 3 radical 2. Now, what would be in the denominator? What would be in the denominator? Well, you have 2 radical 2 times another radical 2. You have 2 radical 2 times another radical 2. Well, radical 2 times radical 2 is 2. Times 2 is 4. Okay. Now, the tangent of theta is sine of theta over cosine of theta. So the tangent of theta is 1 over 3. That's the first of the 2 reciprocal identities, over 2 radical 2 over 3, or 1 over 2 radical 2. How did I do that? The 3's cancel out, because remember, when you invert and multiply the denominator, you invert the denominator and multiply, the 3's cancel out. You're left with 1 over 2 radical 2. And I'm going to see if I can squeeze that in here. Practicing with the radicals, if you multiply by radical 2 over radical 2, you end up with radical 2 over 4. Okay, and finally, the cotangent. Now, rather than taking the cotangent and writing it as 4 over radical 2, I want to take that version of the tangent that we got before we rationalized. Because if we take the reciprocal of that, we get 2 radical 2 over 1, which is just 2 radical 2, and I don't have to bother with any rationalizing the denominators. Okay? So let's take a look at another example. So here's our next example. Given that the cosecant of theta equals 5, find the exact value of the remaining trig functions. This example looks a little scary at first. Again, write out the 6 trig functions in the same order every time. The sine of theta, the cosine of theta, and the tangent of theta. Then the cosecant of theta, the secant of theta, and the cotangent of theta. right? The cosecant of theta is 5. Now, I mentioned this was a little scary. Why? Well, the only trig function value we can really get right off is the sine of theta. Remember, sine of theta and cosecant of theta are reciprocal, so if the cosecant of theta equals 5, the sine of theta equals 1 over 5. Now here's the scary part. I can't find the secant of theta using the identities above unless I know the cosine of theta. Same thing for cotangent. I can't find cotangent unless I know tangent. I can't find tangent equals sine over cosine until I know cosine. So the identities that we have so far don't allow us to find the missing trig functions. Now, the scary part, it goes away very quickly because there are some identities that are going to help us out here. Okay? Well, let's see how one of these additional identities are formed. We're going to take a little side trip here. We're gonna need a couple more identities, a few more identities actually. Let's take a side trip. I want to take a look at a green side trip here. Here's a right triangle, and let's say the sides of this triangle are, let's say it's a 3, 4, 5 triangle. 3, 4, 5 triangle. Okay, and here I put the angle theta in the lower left-hand corner. Now, the sine of theta, remember from SOHCAHTOA? So, sine, opposite over hypotenuse. Cosine is adjacent over hypotenuse. TOA. Tangent is opposite over adjacent. So the sine of theta should be opposite over hypotenuse. I'd rather go back to green here. The cosine of theta is adjacent over hypotenuse. And now I'm not going to write out the tangent or the other 3 trig functions because I don't need them right now. But I want you to notice something. If I take the sine of theta and square it, and to that I add the cosine of theta squared, look what I get. Sine of theta is 3/5 squared, plus the cosine of theta is 4/5 squared. And 3/5 squared is 9 over 25. 4/5 squared is 16 over 25. This is 25 over 25. This is 1. Now let's focus on that for a minute. If I take the sine, for this particular triangle, if I take the sine of theta and square it, and I add cosine of theta quantity squared, I'm going to get 1. Now here's the kicker. Here's the identity. Here's our formulation of this next identity. This always works. Not just for this particular triangle, but for any right triangle. If you take the sine of theta and square it, and you take the cosine of the same angle theta and square that, you add those 2 things up, you always get 1. Always. No exceptions. I want to write that idea in black. If you take the sine of theta and square it, and add to that the square of the cosine of theta squared, you always get 1. That's one of the most important identities in all of trigonometry. This is one of the most important identities. It essentially says that if you know either the sine or the cosine, you can find the missing one. If you know the cosine of theta, you substitute that into this equation, you can solve for sine, and vice versa. If you know the sine, of theta. You could substitute that in there and then solve for cosine of theta. Okay. What does it look like? What does it look similar to? It looks very similar to a formula from geometry. In geometry, we had one that said a squared plus b squared was what? If the hypotenuse c is c, it looks like the Pythagorean theorem. This is called a Pythagorean identity. This is called a Pythagorean identity. Pythagorean identity. There are 3 Pythagorean identities. This one's the most important one. Now, this expression, sine of theta squared plus cosine of theta squared equals 1, happens so often that we abbreviate some of the notation. We write sine of theta squared, which of course means sine of theta times sine of theta. We write for convenience sine squared theta. We also write cosine of theta squared as cosine squared theta. We do this whenever we're squaring a trig function or raising a trig function to any power. If I wanted the tangent of theta to the 7th power, I would write tangent to the 7th theta. Okay, so the first Pythagorean identity can be written as sine squared theta plus cosine squared theta equals 1. Very often, I'll jokingly tell my trig students, which is you, that if I were trapped on a desert island and there was only room for me and one trig identity, this is the trig identity I would choose to be with. It's that important. Okay, so sine squared theta plus cosine squared theta equals 1. So let's go back to our problem. Our problem is, given that the cosecant of theta equals 5, find the exact value of the remaining trig functions. Well, I would like the cosine of theta. As soon as I have the cosine of theta, the rest of the values of the trig functions will simply fall out with using the other identities. I know that sine squared of theta plus cosine squared of theta has to equal 1. But I know sine of theta equals 1/5, so 1/5 squared plus cosine squared theta equals 1. Or 1/25, 1/25 plus cosine squared theta equals 1. Or if I subtract 1/25 from both sides, what's 1 minus 1/25? Well, 1 minus 1/25, 1 is the same thing as 25 over 25. So 1 is the same thing as 25 over 25. So 25 over 25 minus 1 over 25 is 24 over 25. And I want cosine of theta, so I'm going to take the square root of both sides. Now, the values of the 6 trig functions are positive for a while. The values of the 6 trig functions are positive for a while. So for us, we don't worry about the negative square root. Remember, when you take the square root of both sides in an equation, you end up with plus or minus, generally. But here, since the trig functions are all positive for right now, we only take the positive square root. Okay, now back to intermediate algebra. The square root of 24 can be simplified because 24 is 4 times 6. 4 times 6, and the square root of 4 is 2. So automatically I have the cosine of theta is 2 radical 6 over 5. I'm going to go back up and write 2 radical 6 over 5. And I think I mentioned that the other trig functions are going to fall right out. Not quite, but pretty close. The secant is the reciprocal of the cosine. Secant is the reciprocal of the cosine. The tangent is sine over cosine. Remember what happens with the 5 when we divide 1 over 5 divided by 2 radical 6 over 5? Cotangent is the reciprocal of the tangent. And without worrying about rationalizing the denominator for the secant of theta and the tangent of theta, we have the values of all 6 trig functions. So we have a Pythagorean identity. We have a Pythagorean identity. In fact, we have 3. We have 3 Pythagorean identities. The first one, which the one I want to spend the rest of eternity on a desert island with, I think I'd rather have a person or my dog with me, but if I finally get one identity, it'll be sine squared theta plus cosine squared theta equals 1. There are 2 other Pythagorean identities. The first is tangent squared theta. That means tangent of theta times tangent of theta plus 1 equals secant squared theta. And the last Pythagorean identity is that the cotangent squared of theta plus 1 is cosecant squared theta. Okay? So, how do we get that second, for example, how do we get that second Pythagorean identity? How in the world am I going to get tangent squared theta plus 1 equals secant squared theta? I want to show you that. So, I want to look at the first Pythagorean identity, sine squared theta plus cosine squared theta equals 1. And I want to divide both sides. I want to divide both sides by cosine squared theta. So I'm going to divide both sides by cosine squared theta. Okay. I'm going to use some algebra. Sine squared theta over cosine squared theta. Now those squares can be combined to one squaring. So newsflash, a lot of algebra pops up. So from algebra we know that's true. We don't need to worry about too much algebra to convince us that cosine squared theta over cosine squared theta is 1. And 1 over cosine squared theta is the same thing as 1 over cosine theta squared from algebra again. But what's sine over cosine? Now, if you're new at this, it may not be clear. Here's your hint. It starts with a T. Sine over cosine is tangent. Squared is tangent squared. Plus 1 equals, what's 1 over cosine? 1 over cosine, you may not remember it right off, but that's secant of theta. So 1 over cosine squared is secant squared theta. So what I did is I derived the formula for the second Pythagorean identity formula. Okay. So let's practice with a problem example before moving on to our last set of identities. Yeah, it's a long section. This is one of the longer sections for the textbook, actually. Okay, so for example, find the exact value. Find the exact value of each. Each what? Well, I'm going to come up with those things right now. So, for example, part A. what is sine squared of 21 degrees? Oh, I'm putting an actual value of theta in now, plus cosine squared of 21 degrees. What is that? Well, what's the first Pythagorean identity look like? Sine squared theta plus cosine squared theta equals 1. No matter what theta is, sine squared theta plus cosine squared theta equals 1. Now you notice the 21 degrees is the same in both trig functions. It has to be for this to equal 1. So B. What is the tangent of 17 degrees minus the sine of 17 degrees divided by the cosine of 17 degrees? This was a little trickier. So sine, look at the sine of 17 over the cosine of 17 degrees. Let's go way back here, if it's still here. If my surface will allow us to go way back. This is really back. Oh my goodness, I had no idea we had to go this far back. Oh my goodness, there it is. Tangent of theta equals sine of theta over cosine of theta. So the sine of theta over cosine of theta is tangent theta. So the that first tangent of theta, I could leave that alone. But the sine of theta over cosine of theta is tangent of theta. So the sine of 17 degrees over the cosine of 17 degrees is the tangent of 17 degrees. And the tangent of 17 degrees minus the tangent of 17 degrees is 0. Okay, no calculators necessary. We could have gotten this by a calculator. We'll talk about that in the next section. I think it's the next section. Okay. So let's finish up the section. We've learned a few identities so far. We have three reciprocal identities. We have the cosecant of theta is 1 over the sine of theta. We have the secant of theta equals 1 over the cosine of theta. We have the cotangent of theta is 1 over the tangent of theta. 1 over tangent of theta. We have two reciprocal identities. Quotient identities. No, wait a minute. Yes, quotient identities. I forgot their names. The tangent of theta is the sine of theta over the cosine of theta. It's not a good idea for me to forget these since I've been teaching it for 30 years. The cotangent of theta is cosine of theta over sine of theta. Okay. And we have three Pythagorean identities. So what I'm doing right now is basically just giving you a kind of a summary. So we have sine squared theta plus cosine squared theta. Remember that sine squared means sine times sine. Cosine squared theta means cosine theta times cosine theta. We have tangent squared theta plus 1 equals secant squared theta. And we have cotangent squared theta plus 1 equals cosecant squared theta. So we have a total of, looks like 8 identities so far. And I took, what is it? I took about an hour to get those 8 identities. Well, in our last 5 or 10 minutes, we're going to learn 12 more. And don't fret too much. There's a nice device. There's a very nice device for memorizing these last 12 identities. In fact, you're going to learn that there are a lot of devices that we have, shortcut memory helpers for us for getting identities. So we need some terminology though. The first bit of terminology is the concept of a cofunction. Don't panic, it's easy. So we have functions and cofunctions. So if the sine of theta is a function, the cosine of theta is called its cofunction. It's easy to remember this pair, sine of theta, cosine of theta. So what do you expect for the cofunction? I almost gave it away. The cofunction of tangent of theta will be cotangent of theta. So what is the last pair of cofunctions? Secant and what? Cosecant. So now we know what cofunctions are. We also need something from geometry. We need the concept of complementary angles. So complementary angles. Complementary angles are not angles that say nice things about other angles. They don't throw out compliments. Complementary angles are angles like this. If 20 degrees is an angle, 70 degrees will be the complementary angle. If 15 degrees is an angle, then 75 degrees is the complementary angle. If 1 degree is an angle, then 89 degrees is its complementary angle. Okay? So if theta is an angle in degrees, then what's the complementary angle? It should be 90 degrees minus theta. Okay. We also have the same concept for angles measured in radians. So if pi over 6 is an angle, then what is the angle complementary to it? It won't be 90 minus theta. It will be the corresponding angle measured in radians minus theta. So pi over 2 minus pi over 6. Well, pi over 2 is 3 pi over 6. Minus 1 pi over 6 is 2 pi over 6, which is pi over 3. So if pi over 6 is the angle and pi over 3 is the complementary angle. So it's a little tougher to find complementary angles in radians. So if theta is an angle in radians, then pi over 2 minus theta is the angle, complementary angle. So now we know what cofunctions are. Cofunction of sine, cosine. Cofunction of tangent, cotangent. Cofunction of secant, cosecant. Now let's look at getting those last 12 identities memorized somehow. I'm going to draw a triangle from geometry. It's a very standard triangle we learn about in geometry. It's called a 30, 60, 90 triangle. 30 degrees, 60 degrees, 90 degrees. And the sides, corresponding sides, are going to be 1, 2, and radical 3. Remember from geometry, we were asked to memorize this angle. No, this triangle, rather. Now, I want you to, with me, remember, first of all, the SOHCAHTOA device. SOHCAHTOA. And with that device, what is the sine of 30 degrees? Sine is opposite opposite of 30 is 1 over hypotenuse. The hypotenuse is 2. So the sine of 30 is 1/2. 30 degrees. It's 1/2. Now, what is the cosine of 60 degrees? Well, the cosine is adjacent to the angle. The adjacent is 1. The adjacent to 60 is 1. And hypotenuse is still 2. Now, the sine of 30 is 1/2, and the cosine of 60 is 1/2. Eliminate the 1/2. The sine of 30 equals the cosine of 60. This relationship always works. Now, what do I mean by this relationship? Sine and cosine are cofunctions. Cofunctions. 30 and 60 are complementary angles. Here are all 12 of our last identities. Complementary. Cofunctions. Cofunctions of complementary angles are equal. That's 12 identities. That's 12 identities in one statement. How can that be? How can that be even one identity? Well, you'll see that in a minute. Let's name this. This is called the Complementary Angle Theorem. The Complementary Angle Theorem. It's a shorthand for all 12 of these last identities. What does one of these identities look like? Well, it's not sine of 30 equals cosine of 60 because identities have a variable angle in them. Sine and cosine are cofunctions. Theta and 90 degrees minus theta are complementary angles. Cofunctions, sine and cosine, of complementary angles, theta and 90 degrees minus theta, are equal. That's an identity. It's always true. So, where are the other 11 identities? Well, here's another one. The tangent of theta equals, what's the cofunction of tangent? Cotangent. What's the complementary angle of theta? 90 minus theta. There's 2 out of 12. You don't have to memorize all 12. Cofunctions of complementary angles are equal. Secant, cosecant, theta, 90 minus theta. There's 3 out of the 12. Another one, cosine and sine are cofunctions. Theta and 90 minus theta, 90 degrees minus theta, are complementary angles. Cotangent and tangent are cofunctions. Theta and 90 degrees minus theta are complementary angles. They're equal. There's 5. 6. What's the last one? Cosecant and secant are cofunctions. Theta and 90 degrees minus theta are complementary angles. So there's 6 of the 12 identities. How could there possibly be 6 more? We only have 6 trig functions. How could there be 6 more? These are the six identities for the complementary angle theta for degrees. We have another 6 for what? Radians. Name 2 of them. Sine and cosine are cofunctions. Theta, radians now. Pi over 2 minus theta. I'm not going to write out all 6 of the remaining trig functions. Well, here's one more. Cotangent and tangent, just like the one above, cotangent and tangent. Theta, no, we're dealing with radians. Pi over 2 minus theta. Okay. I have a note to myself that all 12 of these identities are on pages 124 and 125 in your textbook. I hope it's for this edition that I wrote that down, but okay. Okay, so here's our last example to finish up the section. Example. Find the exact value. Find the exact value. A. Cosine of 40 degrees over the sine of 50 degrees. Well, each of these numbers, cosine of 40 degrees and sine of 50 degrees, are very complicated numbers individually. We would need a calculator to compute those numbers individually. However, I know that cofunctions of complementary angles are equal. 40 and 50, they're complementary angles. They add up to 90 degrees. Complementary angles add up to 90 degrees. So let's use the complementary angle theorem. Cosine and sine are cofunctions. 40 and 90 minus 40, which is 50, are complementary angles. So cosine of 40 equals sine of 50. I'm going to leave the sine of 50 alone in the denominator, and that's 1. Okay. Let's see. Let's take a look at one last problem. This one's going to be kind of complicated. This is the most complicated one. So let's take a look at, let's say, tangent squared 5 degrees plus 1 minus cosecant squared of 85 degrees. Wow. Look at how complicated that is. Now I'm going to help us out a little bit, because these identities that we've learned, there are quite a few of them so far in this one little section. And so I'm going to give us some help. One of the Pythagorean identities said tangent squared theta plus 1 is secant squared theta. So I can use that identity to start us out. Oops. So tangent squared 5 degrees plus 1 is secant squared 5 degrees, because tangent squared theta plus 1 is secant squared theta, minus, I'll leave the cosecant squared 85. Well, we've shrunk it down a little bit. Not quite there. Now, notice 5 degrees and 85 degrees are complementary. So I'm going to use the complementary angle theorem. Cofunctions of complementary angles are equal. Secant and cosecant are cofunctions. 5 and 90 minus 5, which is 85 degrees, are complementary. So secant squared of 5 degrees is equal to cosecant squared of the complementary angle 85 degrees. But remember, this is minus another cosecant squared of 85. That gives us 0. Okay. And this officially ends a very, very long section. We have a couple of long sections, really long sections in our course. This is one of them. This is not typical that sections are quite this long. So this ends section 2.2, the trig functions of right angle trigonometry. Okay, and I'm looking forward to talking with you all again soon.